Projective spaces and projective varieties. But today and the next lecture is about still about affine. I will use the results which we have proven, not a normalization lemma in different aspects, to prove important theorems about how you should work with algebraic affine varieties. Okay, so the first you have these finite projection maps. So if you have a algebraic subvariety in Cn, then it could be projected. There is a projection, and in fact there is a big set of projections, lots of different projections to C power d, which is finite and dominant. And this is something we have already done, so I would probably skip it because you have seen that a lot. Okay, there was an issue last time, how you prove notable normalization for non-irreducible varieties, because I used it, so let me just show you how to prove it. In fact, this is more or less in the I mean, most of what I wrote here you already had from the test 2 weeks ago, or 1 week and 1 day ago. Theorem, it's the previous theorem, but stated for non-necessarily irreducible subvarieties. Suppose you have x, which is union of xi. In Cn, this is irreducible decomposition. Irreducible decomposition. Then there exists a projection from x to C power d, which is finite and dominant. Well, finite and dominant. Or you can say that it is dominant on the component of biggest dimension. Because, well, we didn't define dimension, so it's better to say that it is dominant. And the proof is very simple. There is a trivial observation which you did already have in the tests, that okay, you have x is equal to union of xi, all xi algebraic, and this means that they are given by ideal. Say, what is the notation here? Do I have any notation? M. Well, ideal Mi defines your xi. So O xi is Ox quotient by Mi. You have a map. O xi direct sum goes to direct sum. Ox quotient by Mi, which is direct sum of O xi, and this is the same as just function on the disconnected sum of xi. Okay, this is finite because each quotient map is clearly finite, and this is just direct sum of different quotient maps. It's also dominant for a clear reason, and also if let's prove actually that it has no kernel. If f belongs to kernel of this map, say called psi, then f vanishes. It vanishes in all points of xi. So it vanishes on all points of xi, and then it vanishes f is equal 0 on x, and this means that f is equal 0 by definition, because regular function on x is precisely functions, it's the restriction of polynomial functions. Okay, so we don't need even Hilbert-Nullstellensatz here. Well, you can use it, but it's not needed. Okay, now we have projection. Take projection. Pi from Cn to Cd, which is finite on all xi. Such a projection exists because, this was something we know already, that if transcendental dimension of x is bigger or equal than d, then general projection is finite. And general in the sense of being outside of a subvariety, which is measure 0, because it's zeros of polynomials. Okay, we took projection. It's finite on all xi, and it is, and is dominant on one component. I think this is what is stated here, right? No, here we didn't even say that it is dominant at all. But yeah, here is k and here is k. Dominant on one component. Okay, anyway, there exists such a projection. And then you take a composition of, so you have OCN goes to O x, and this goes to this goes to O x I direct sum. This is an embedding. So if this is finite, this is also finite because everything is Noetherian. We know that intermediate, if you have two finally generated models, all intermediate models are finally generated. So this is finally generated over this. Okay, and this is very routine. So every time you prove some theorem about irreducible, you can extend it to non-irreducible by doing this kind of decomposition. It's easy. There is nothing non-elementary here. Okay, integral closure. This is something you know. The important thing about integral closure that factorial rings are already integral closed. Should I remind you about integral closed things? So the idea is that integral closed means that if you have a solution of a monic polynomial equation which belongs to fraction field, it belongs to your ring. This is what it means that it is integrally closed. And the important thing, that something we have proven, that integral closures, it will be in the next slide. In fact, integral closures of algebraic varieties are finitely generated. This is this result. You have an affine variety, you take integral closure of ring of regular functions, then it is finally generated. In fact, it's finally generated as a model over your ring K. Should I give you an explanation of that? Anyone? Okay, I might, because we have done that several times, but it's not a big deal to repeat it. Okay, so let me define. You have a ring A, I hat is integral closure, if A hat is a set of all, say, R inside the fraction field. This is fraction field. Such that A of R is finally generated A model. This is, of course, equivalent to R being a root of monic polynomial P of t inside A of t. I think for that to make sense, you have to assume that A is without zero divisors. But you can extend everything to rings with zero divisors, it's not a big deal. Okay, am I clear? So theorem, if A is finally generated over C sub, for instance, then A hat is finitely generated as A model. And of course, this means that it is finally generated as a ring as well, because you just add generators of A hat over A to the set of generators generating A. The proof is not hard. So the idea is that you have to have something which is already maybe you don't have any idea of how the how this integral closure works, but we know something. We know that for factorial rings, it is integral closure is the ring itself. So what we shall do, we consider A using the Noether lemma as finite, it's finite OCN model. So it contains this, and A is finite OCN model. This is Noether normalization theorem, right? This we can do. And now, and everything is dominant, say. Yeah. Generally speaking, you would have, since you have a morphism from spec A to spec Cn, you would have a map from here to there, but in fact it's injective because we assume that it is dominant. Okay, and now you have, we use this result which I quoted previous slide, which says that if you have a ring which is integrally closed, you take its fraction field, you take finite extension of this fraction field, and you take integral closure of this ring inside the finite extension, then it is finitely generated. So if you have K of B over K of A is finite extension, and A hat is equal A, for instance, and then B hat, this extension of B, integral extension of B, is finitely generated over A. So to see that, you use essentially trace. You pick, you know that this is finitely generated space over K of A, K of B, so you pick the basis which is in B. Then you use trace form and use dual basis, and you obtain that your B is intermediate between two finely generated models. It has to be finely generated because of Noetherianity. So you have to assume that A is Noetherian as well. This is part of assumptions. But finely generated are always Noetherian, so it's not a big deal. Okay. And then we can apply that because so you have a hat. So this is finite. So this is K of A is finitely finite extension of K of Cn. Of polynomial functions, OCN. Finite. You apply this and you obtain that A hat, the integral closure of A, is finely generated over OCN by this result as a model. And this is called normalization. So definition, if A is finitely is spectrum, is OX, where X is a affine variety, then it's integral closure. We know that finely generated rings are the same as affine varieties. Well, spectrum, if they have no nilpotence. Spectrum of A hat is called normalization of X. Questions, comments? Anything clear? Okay. So this is again about normalization. Well, the important thing about normalization is it's finite and birational. Birational means that it is isomorphism outside of closed complex analytic, closed algebraic subset. Okay, and finite surjective. Okay, good. Now I can finally state the Noether normalization lemma, the version which I need. It's a really important and useful theorem. And it was proven last time, or previous time. Okay, so you have X inside Cn, irreducible algebraic subvariety. Okay, then there exists x1 inside C. Let's assume that D is transcends dimension, transcendence dimension of X over, if you remember, transcend dimension is dimension which we use to define this define projection map in Noether normalization lemma. So this means that you can, this precisely means that you have a finite dominant map from X to C power D. Okay, then there exists X1 inside C D plus 1 such that given by polynomial equation, given by polynomial, just one polynomial equation, P of T is equal to 0, where P is a polynomial over a ring of C power D. So this means that you have a polynomial equation with polynomial coefficients, and you can think of that as like for general point you have precisely if this degree m, for instance, then you have m solutions for each point here, because it's a monic polynomial. They say monic, I should say it monic. Since it's monic, it has precisely m solutions for each values of parameter. Well, some solutions could be multiple, of course, but okay. And yeah, X is isomorphic. Well, normalization of X is isomorphic. Do you assume that X is normal? Normalization of X, of course, because there's assumption that X is normal is missing. So normalization of X is equal to normalization of X1. It's not hard. You just consider this field, this finite extension. So the proof is proof. You take k of x, which will be, this is by the previous result, which will be finite over k of C power D, finite extension. Then this means that by the theorem of primitive element, this means that you can just generate it by one element, and this field is so k of k of x is k of C power, the field of rational functions on C power D, quotient, and then you take polynomials and you quotient by P of t, where P of t is monic. Okay, then you multiply it yeah, you take integral closure of C power D in that field. This integral closure now is generated by monic polynomials. You can assume this is monic because everything is finitely yeah, and now anyway, this k of x now have this, it has the same fraction field as the solutions of this equation. This is why it is this is why it is they have the same normalization, because normalization is uniquely determined by the fraction field, as long as this fraction field contains this ring. Okay. Now I'm just reminding you something. This is not something I would need, but it is mostly like for historical context. So we can really define a multiple valued function formally, but it's better to do it in complex analysis and not because it's a historically complex notion. So we define complex variety as the usual way. Well, you have two different ways, but they're equivalent, like with usual manifolds. You define complex manifold as a manifold which has an atlas covering this a cover with the open sets are identified with the open ball in Cn, and the transition functions are complex analytic, complex differentiable. And then this is the same, of course, as we had the definition in terms of sheaves, if you remember. We defined manifolds as spaces with sheaves which are locally isomorphic to open balls with smooth functions. Well, now it is open balls with complex differentiable functions. This is complex manifold. Now you have notion of complex variety. So variety given by a collection of complex analytic equations. So for whom it's completely clear. Not everybody is very happy. Okay, then I would probably go slow because it's really useful notion which you always have in theory of Riemann surfaces. So originally Riemann surfaces were multiple valued functions associated with some things like, from complex analysis, like logarithm. So definition. So holomorphic, first holomorphic function is complex differentiable. In other words, it's a function from Cn to Cm. You take its differential, and this differential is complex linear. And then you have M complex manifold if there exists a cover Ui of M, if M is a manifold, the usual sense, and there exists a cover such that Ui are all identified with open ball in Cn, and transition functions from one, so you have coordinates, you can go from one coordinate patch to another. Transition functions are transitions between these coordinate systems. Transition functions are holomorphic, complex differentiable. Okay, now you can define, this was the manifold, now we can define complex analytic subvariety or variety. So M or Z inside M, complex analytic subvariety. It's slightly badly worded. Complex manifold locally given by collections of complex analytic equations. Sorry. So globally, you might have no global holomorphic functions at all. It's bad idea to define something globally in complex analysis or algebraic geometry. So you have complex analytic variety locally defined by finite system of complex analytic equations of complex analytic. Complex analytic is the same as complex differentiable equations. P1 of Z is equal to P2 of Z is equal to, and so on, is equal to Pk of Z is equal to 0. I mean, this is the same as with polynomials. I mean, for usual algebraic geometry, you just replace polynomials by holomorphic functions, and the same notions work. And this is actually how it works at all. I mean, the whole thing, the whole algebraic geometry can be moved to complex analysis by just shifting of definitions. Okay, now we can define multivalued function. Definition. Multivalued function from X to, say, C. You don't need C. You can actually take other or other subvariety instead of C, but let's do variety. Let's do with C on a complex manifold X. Manifold X is a subvariety, complex subvariety, obviously, say Z inside X times C, such that closed complex subvariety. Closed means that, this means that you have this property even for limit points, because otherwise you can just like erase something, remove it, and say that, okay, this is not our points, we don't care about them, and we care only about points of our subvariety. Do something like you have a subvariety, and then remove part of it, close subvariety. You remove part of it, and just say that you don't care about these points. This is bad, because this procedure of removal can be very traumatic for your variety. Okay, so variety closed such that projection from Z to, let's call also reducible. Irreducible, and irreducible are defined the same way as for affine. Projection from Z to X is generally a local diffeomorphism. Okay, what does it mean, local diffeomorphism? This means for each point of Z where it is local diffeomorphism, you have several preimages, and for each preimage, the neighborhood projects to X bijectively. And each of these preimages is called a branch of your function. So you have like function which has several values, but locally these values can be moved around, and it's like a collection of functions. So when you think of these guys, you should also think of them as multi-valued functions. Okay. Now let me give you examples. So there are lots of examples which are actually belong to algebraic subvarieties. For instance, you have a map X, well, y goes to square root of X. Of course, this is not globally defined function on C. But the corresponding graph is well defined. So the graph is X is equal to y squared. And of course, around a point which is non-zero, this is locally, the projection is locally diffeomorphism, because if you have a function, you can define, you have a point, you can define square root if you choose a branch. Square root is defined up to plus minus 1, of course. But if you fix the point in a neighborhood, you have this choice made for you already. Yeah, of course. It will be in the next slide, in fact, I would prove it. And another example is logarithm. Y goes to logarithm x. Again, this is not well defined on C. This is not a function, because logarithm, you have to choose a branch. But if you consider its graph, it's well defined. You take exponent of y is equal x. This is a z. So the z is just solutions of this equation inside c squared. It's well-defined subvariety, and you projecting this subvariety to y, you obtain all branches together. Okay, this is how you work with these funny algebraic functions like collection of roots of a polynomial. You think of them as of multivalued functions. Okay, and now, thank you very much for reminding. This is inverse function theorem. We had it already, in fact. So, it tells us it's a criterion for having a diffeomorphism. So, theorem, if you have a map f from M to N, M and N are n manifold, n-dimensional manifold, or k-dimensional manifolds. And you have a point z, say, m small and m big, such that differential of f at this point is invertible. Differential is generally a map, df restricted to M, is a map from tangent space to M, to the manifold M to T f of M n. This is two n-dimensional spaces. If this is invertible, then f is locally a diffeomorphism in a neighborhood of M. Right? This is something we had already, and you should know this. I'm not, unless you want me, I'm not going to prove it now. But I mean, it's in the lectures. I think it's lecture 5. Okay, and I have another, I'm going to use another result, which is version of this theorem. This called like inverse function theorem, and this called like implicit function theorem. It's about a preimage, a variety given by a set of equations. So you have f. Well, let's start with definition. You have f from M to N, M and N manifolds. Here it's stated for Rn, but it's local, so it doesn't matter. X M inside M big critical what? Critical point if df not surjective. In this as a map, so we take restricted to M, consider as a map from Tm of M big to T f of M of N, and it's not surjective as this map, and M is critical value if there exists, sorry, M, of course, it's a value, so it's in N. So let's call it X in N. Critical value if there exists M inside M big, critical point, such that f of M is equal X. And regular otherwise. Regular if it's not critical. Non-critical. Okay, now I can state.
The dimension of M is greater than the dimension of N?
Not necessary. I mean, then just empty. Preimage should be empty. That's all.
Shouldn't you define then the critical point to the point where the derivative is not has not the maximum possible?
No. If dimension of M is less than dimension of N, then all values of N of M are critical, but there are lots of points which are not values. And they're regular values, which just not in the image of M. So the theorem of Sard, it makes sense, perfect sense in in the generality, which says that critical values have measure 0. And they are measure 0 regardless of dimensions. This is always true. So most values are always regular. I'm not going to use that, but it's really a useful result. So theorem. If you have f from m to n, and x in n is regular, then f minus 1 of x is a submanifold in M. Okay, this is also true when it is empty. It's okay. It could be useful, in fact. But what is this is a standard construction of submanifolds. We have done it, and what is important is that you can easily deduce this theorem from that theorem, just adding extra variables. So if if dimension of M is less than dimension of N, this is just an empty statement. If dimension of M is equal to dimension of N, this is precisely this statement because it's locally diffeomorphism, so the preimage is discrete. And finally, if dimension of M is bigger than dimension of N, you just add extra variables and apply this. Just artificially add extra variables so that your map F becomes, you add extra variables here, your map F becomes a diffeomorphism, and then you take preimage of the set where these values are vary and the points in N don't. And this will be precisely your subvariety, submanifold in N. Clear? We had that. So it was in, again, section 5, we did, lecture 5, we did it. So if you have questions, please ask, otherwise I'm going on. Good. Okay. I'm now going to give you something like slightly more elementary, and there will be a better proof of the same statement later. I mean, more shorter and more explicit, but let's do it now, like in the most elementary way. Oh, Z smooth is wrong. I'm sorry. This is a misprint. Okay, theorem. So suppose you have map a polynomial P of T. Okay, now let me do this. Give you the following convention, which I will always keep. So I consider C power n plus 1 with coordinates z1 dot 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 zn and t. And this set of coordinates is called z. Z is just collection of coordinates from 1 to n. Okay, so now you have polynomial P of zt, which belongs to C to OC D of T, n. So this is a polynomial on T with coefficients which are polynomials in the first n variables and values, and I assume that P is monic. And then do you see that? In fact, you don't need that. Okay, it's monic and irreducible. Irreducible. Then you can consider Z, it's zeros of P ZT. Then you have a projection map. P from Z to CD, this multivariate function, to Cn, is a multivariate function on Cn. You see, multivariate functions are in fact not functions on Cn, they are functions opposite way. It's like for each point I have several preimages, and these are your multiple values. Make clear? Okay. Let's prove it. So to prove it, you have to do you have to check first that that this sub-thing has smooth points, and second that it's locally diffeomorphism. Because our what we need for multiple valued function, we need that general point is locally diffeomorphism outside of dense set, and this is what we're going to prove. We're going to prove that at least this is smooth some general point, and the general point, in fact, its projection is locally diffeomorphism. Of course, we shall use the inverse function theorem first. So you have proof. Step 1. You have your projection pi from Z to Cn, and need to prove, to show that the differential Z is given, so we need to show that Z is generally smooth in general point, but Z is given by this polynomial equation P of Z t is equal to 0, and we apply the inverse function theorem, and we notice that this is smooth at each point, at each zt inside Z, such that dp, the differential of this polynomial at this point, zt, is non-zero. If it is non-zero, it's clearly surjective because it's it maps to something of dimension 1. If it's not 0, it can be non-surjective. Okay. This is smoothness of Z. Let's check it. There is a very simple way of checking it. There will be a better way next slide, but let's do it like the simplest possible way. So you write so you write P of Zt is equal to sum, and here you have okay, this is monic, so you have t power n plus sum ai t power I from I equals 0 to n minus 1. And I, all the coefficients belong to polynomial functions in Z, in the first n variables. So dp now of Zt is t power n minus 1, n minus 1, t power n minus 1 dt, plus you have this sum of t power, well, from I equals 0 to n minus 1, I times t power n I minus 1 times ai plus sum from I equals 0 to n minus 1 d ai and dt I, of course, dt. Here you have d ai times t power I. Anyway, if we're interested in the top degree component, we can erase. We are interested in for very big T. Just want to check something, like make simple check. So we consider T very big, so we're interested only in top power of T. And so we write here T n minus 1 T dt plus, now you have dAI T power n minus 1 plus O of T power n minus 1. O small. Right? Okay, and here these two are, I mean, this depends only on Z, and this depends only on T. This is not zero. So the dominating part is non-zero already, and the rest are just so small that they don't affect the result, and this means that this is always smooth. Okay, next slide you will see another proof. So don't worry if you don't like this. But it's useful just to have like big terms, small terms. Let's see how it grows, and this gives you a solution almost immediately. Anyway, we know that there are smooth points. Now, let's take a smooth, or in fact any point. Okay, we don't need this. You take a point zt inside Z. This is zero set of our polynomial, and it is smooth if dp restricted to the tangent space to zt of Z is, well, to Z tangent space to inner point zt to Cn plus 1 is non-zero. This is something we already seen, and it is projection is so you have a projection. So the tangent space, for this point, tangent space in the zt of Z is equal to kernel of dp. And it is regular if the projection from tangent space to zt of Z to tangent space of in Z to Cn is invertible, has no kernel. But what is its kernel? Its kernel is a point 0 tau, where 0 is like point in Cn. This is kernel of this map. So we need to show that the kernel of, no, we need to find all points where the kernel of this map is 0. Okay, and but what does it mean that 0 tau belongs to kernel of P of ZT? This means that the derivative so if dp applied to this is non-zero, this means that it's the derivative of p along t. I mean, if this is 0, then this means that the derivative of p along t is 0. This is equivalent. This is equivalent to dp by dt of zt is equal to 0. All right, because I mean this is the component in the derivative in the differential which has t part, and sorry, which has t part. because it's derivative along t. And okay. We finally got to the following trivial observation that Z is smooth and projection from Z to Cn is diffeomorphism in neighborhood of any Zt such that dp of Zt by dt evaluated at Zt is non-zero. Good. Okay, now let's prove that there are lots of such points. It's not hard. So prove that they exist. Okay, I think this can be erased now. We don't need it. So suppose that P prime of Zt vanishes. Well, generally speaking, it would be a divisor, right? Because it's another regular function on Z. But then if it is divisor, fine. Then it is obviously has its measure 0 because it's just zeros of some polynomial function. The problem is that it could be vanish everywhere. If this vanishes everywhere on Z, okay, then you can use Hilbert-Nullstellensatz because Z is irreducible and given because of irreducibility of the polynomial by equation P of Zt equals 0, which is a reducible polynomial, and if you take the ring O of C power n plus 1 quotient by P, it's again has no other divisors. Here we use that it is factorial ring, which we proved. Okay, but if this vanishes by Hilbert-Nullstellensatz, if P prime of Zt is equal 0 on Z, then by Hilbert-Nullstellensatz, this implies that P prime belongs to this ideal, to the ideal generated by P, which is impossible by degree reason. Impossible because of degree. Okay. Let's have a break now. You have like 5 minutes until 38, according to my timing. Just short break. If you have questions, please ask. Otherwise, we shall be back in a few minutes. To look at this function in detail. For that, I define you, I do some manipulation of symmetric polynomials. So how many of you know about symmetric polynomials? Almost everybody. So symmetric polynomial is a polynomial which is symmetric under permutations of Zi. And then if you have this definition, sigma n invariant polynomial, or P in C of Z1 dot Zn is called symmetric. And there is examples of symmetric polynomials. Example, you have product of T minus Z plus Zi and coefficients from I equals 1 to n, coefficients of this. So let's write it like sum of EI T power I from I equal well, 0 to n plus 2n. And coefficients of this is called elementary symmetric polynomials. Of these are called elementary symmetric polynomials. And the important thing that theorem, which you can prove as an exercise, it's not very easy, but it's not hard. You can sit and just do it by induction, that all symmetric polynomials are expressed polynomially as polynomials on EI, on these elementary symmetric polynomials. Clear? Questions, comments? Okay, I don't have much time now, but this is something you should probably know from like elementary algebra. Now I define. So how many of you already know what is discriminant? Please raise a hand if you know. Okay, so the discriminant is a quantity which measures how far your polynomial is from having multiple, roots. So if all roots are simple, discriminant is non-zero. So take product, you have a polynomial p t minus zi from I equal 1 to n, p of t. And then you consider the following quantity, d. It depends on z1 dot zn, and it is equal to product from I not equal to j, zi minus zj. Notice that each term here occurs twice because you have I and j, you can exchange them. You will have, so it's like minus squares for I less than j. This is symmetric. Symmetric. Then it is expressed through coefficients. Coefficients of p, right? By this theorem. Clearly, this is symmetric because all permutations keep this polynomial. And, well, there's examples. So discriminant of quadratic polynomial you have seen a lot because it's something which you study in school when you solve the quadratic equations, b squared minus 4c. And discriminant of cubic polynomials are here. You might encounter it as well if you studied cubic equations. Okay, so definition, discriminant of p is d of e1 dot en minus 1. Notice that if you have n guys here, there's n minus 1 coefficients because the top is just 1. Expressing this star through coefficients. And it has some obvious properties. The first property is just trivial observation. It's a claim, and I'm not going to prove it because it's obvious that claim p of z of t has no multiple roots if and only if d of p, so it's d of p, you can think of it as d of p, is non-zero. Okay, if all these guys are different, then discriminant is non-zero. If some of them are equal, then discriminant is 0. So this is nothing to prove. And the second is slightly, in fact, if you heard about resultants, then discriminant is a resultant of between p and p minus 1. But I'm not going to use it or to prove it. I'm just giving you the trivial corollary. So which like elementary, and then you can actually use it to prove that this is resultant if you know definition of resultant. Corollary that suppose you have P of t K over some field, a polynomial, and I assume that K is algebraically closed. Then derivative pi prime of t vanishes at roots, some roots of p. This happens if and only if d of p is equal to 0. This is equivalent. So proof. Okay, let's A be a root, or alpha is a root of P. Then you can use P of t. You can use division with of polynomials. All right? Am I understood about division? Okay, and then P of t is equal to 1 minus t minus alpha times P alpha of t, where P alpha is another polynomial. P alpha is polynomial of smaller degree. Okay, now let's take its derivative. P prime of t is equal to P alpha of t. Here I take the derivative of this, and then I add plus t minus alpha P alpha of t prime. Okay, and then P prime of t is equal to 0. This is already equal to 0, so it doesn't contribute. So P prime, let's evaluate this at alpha, and this will be equal to P alpha of t. Okay, so this is equal. This is P prime of alpha is equal to 0, if and only if P alpha of alpha is equal to 0. This is equivalent to P being divisible by 1 minus t square. So this is 0 if and only if alpha is double root, at least double, maybe triple. Okay, and we're done. Because if P prime doesn't vanish, you have no multiple roots. If P prime vanishes at alpha, we have multiple roots. Clear? Okay, good. Now let's go for the main important theorem. Suppose you have P of z t is a polynomial with coefficients in, so it's OCN of t, monic. And d, which is a, I mean, what is these coefficients of these polynomials are polynomials on Cn, and discriminant is a polynomial expression of these coefficients, so it also is a polynomial on Cn. You can think of it as a section of Cn. It's discriminant. Okay, now you have U is Cn without zeros of D. This is an open dense subset, unless the well, if it is irreducible, if it's irreducible, it can't have the multiple roots, because if it has multiple roots, we use the same argument as previously. Then the derivative vanishes at the zeros of p, and then derivative, since everything is irreducible, this implies that this can't happen if p is irreducible. Okay, you remove zeros. You take z is roots of zero set of p. It's projected by the map p to Cn, and we consider the map pi from z without okay, so this is u without pi minus 1 of u goes to u. Then this is finite, like d. D is dimension of degree of p. This is finite d-sheeted cover of u, and then z is smooth. Z without this set, pi minus 1 of u is smooth. So you really have this is something we discussed a lot last lecture. We have a finite cover. Proof is surprisingly simple. So we start with a point zt inside this set, z without pi minus 1 of u. So it's a point where discriminant is non-zero, and then pi prime is non-zero. Pi prime of zt is non-zero. This is by corollary 1, which is here. If discriminant is non-zero, then there are no common roots of these two guys. So on each root of this, which is point in z, this is non-zero. Okay, and then, as we have already discussed, the derivative of the projection pi restricted to z from tangent space to z to Cn is isomorphism. Because its zeros only exist in, it can have zeros only if derivative of p vanishes. And it doesn't vanish. Okay, then it is local diffeomorphism. Yeah, so this is, so this means that z without pi minus 1 of u is smooth, and a projection locally diffeomorphism. Okay, and then you just notice that step 2, it's step 3 now, but I somehow, you have a map from z without pi minus 1 of u going to u. It's each point has deep images and locally diffeomorphism. This already implies that it is a covering, because, okay, what might a priori happens with covering is some point disappears. But this is impossible, because it's precisely the preimages, so nothing can disappear. There is no such thing as you have like covering and then you remove a point. No, this can't happen. So this is really, it's not hard. It's like general topology, point set topology result that if you have deep preimages, it's precisely the cover. Okay, I'm almost done. We have 5 minutes. Let's apply that, get something. Next time I will apply more, but let's do, we can already start milking this result. Okay. So now, for instance, we can prove that every algebraic variety has smooth points. Okay, so corollary. Suppose you have X algebraic variety, affine variety. You have a finite map, then there exists a finite map from X to Z, finite birational map. This is our normalization, in fact. And divisor D in Z, such that Z without D, and divisor D prime in Cn, such that Z without D to Cn without D prime, or D1, is finite covering. This is what we proved, right? We just proved that every variety is isomorphic to something which is defined by a polynomial. And then we proved we classified the varieties which are defined by polynomials, proving that they're all have this form. So it was already proven. Okay, and the corollary that every algebraic variety has smooth points. Well, these birational maps. Birational map is, we have proved that it is isomorphism outside of a divisor. So this is an isomorphism outside the divisor, and this is smooth. Has smooth points. Moreover, it is smooth outside of algebraic subvariety, proper algebraic subvariety, proper algebraic subvariety. Okay, why it is smooth outside of proper algebraic subvariety? This is because X is mapped to Z. This is an isomorphism outside of a divisor, and Z is mapped to Cn. This is covering outside another divisor. Let's remove both divisors. So we take pre-image of D to X and remove the divisor where it is non-isomorphism and the divisor then where this is ramified. This is called ramification divisor, by the way. Okay. Now I'm done. Next time I will give you the dimension theory, because it's really useful. You should prove everything just by using induction by dimension. This is how it is done.